let's very briefly recapitulate some of the key aspects of what we've learned so far. On the one hand, we have systems, which we represent with blocks. Blocks such as this one. And a block is just a model of a system. And on the other hand, we have signals, which we represent with arrows. We have here this signal, u of t, which is an input to the system. And another signal leaving the system, y of t, which is as a consequence an output of the system. And the system, what the system does is to act upon the input to produce the output. And it does so according to certain law, to certain rule. Well, sometimes the rule that defines the system is static, and sometimes it is dynamic. So, for example, a static system could be this one. We have an input x1 of t, and the system, and maybe the system has a second output, which we could call x2 of t, and the overall output would be x3 of t. Okay, a static law could be, for example, the output of the system is equal to the first input, u1, plus u2 squared. This would be a nonlinear static rule, because the value of the output at each point of time depends on the value of the inputs at that same point of time. Well, an example of a dynamic system, or a system governed by a dynamic rule, could be the second derivative of y plus y squared is equal to 2 times u. This is a nonlinear differential equation, and maybe this is relating the signals x4 of t and the output x5 of t. Okay, so we also know that we can connect systems, and doing so, each one of these two would become a subsystem, just part of a bigger system. So in this case, for example, we could adapt these two signs to produce a third one, which we could call x6 of t. Well, this adding point is actually, or it can be seen just as another system with a linear static rule, that would be y is equal to u1 plus u2. But we don't use blocks for that. We normally use this circle representing a summing point. So we can continue doing this. We can keep building a big block diagram, including many subsystems. So let's go with a linear dynamic system. For example, in this system, the first derivative of the output plus the output is equal to 2 times the input. It is almost the same as the other one, but this is a linear differential equation, and this leads to x7 of t. And maybe the output of this system, or this block, or this subsystem, could pass through another block, which is in which the operation that is performed on the input is the convolution. So maybe here the output y of t is equal to the convolution of the input u of t convolution asterisk g of t. And we know that this is an external representation of a linear system, just as this one. But this here is an external representation. And again, maybe the output of this system can be added up with some other input. Let's call it x8 of t, and this is x9 of t, and the result is x10 of t, and this could pass through, for example, through an integral from 0 to t of u dt. This would be the output of this system. Okay, this system is just an integral, and its output would be, let's see, x11 of t. So we could go on and on with this, building a big system by means of separate blocks. And again, remember that some of these blocks may be internal descriptions, that is, there's no ambiguity, and some others may be external description. But regardless of whether the description in the blocks is internal or external, if in our diagram there are only linear operations, and I mean linear in a dynamical sense, so for example, in this case, this would be a linear operation, and this would be a linear operation, and also this one is linear, this one is linear, and this one is linear. So if we have a system just with those kind of operations, we can Laplace transform the diagram. We can take the diagram to the S world, to the complex numbers world. So let's do so by applying the Laplace transform on the operations that are represented by the blocks. We'll begin here. The Laplace transform of the sum is obviously just another sum, and the input would be x5 of s and x3 of s. Now we can Laplace transform this differential equation. We would get y of s times s minus y at 0 plus y of s is equal to 2u of s, which means that the output y of s is equal to 2u of s plus the output at 0 over s plus 1. How do we represent that here? Well, it is very simple. We just write here a block with 2, then we add y at 0, and then we multiply everything by 1 over s plus 1, and the output here is x7 of s. Okay, great. Here we have a convolution, and we know from the properties of the Laplace transform that a convolution transform is just a multiplication. So here we'll just write g of s, and the output of this will be x9 of s. Here again we have a summing point with x8 of s. The output is x10 of s, and the transform of an integral is just 1 over s. 1 over s. And here we have x11 of s. And now we have everything transformed to the s world. And the key point here, the way we have to read the diagram, is by realizing that the output of each block is just the multiplication of the input by what is inside the block. So, for example, here x9 is just the multiplication of g of s times x7 of s. x9 of s is just g of s, x7 of s. And the same thing happens here, and the same thing happens here. So, in a way, all blocks become transfer functions. Can you see that? All blocks have become transfer functions because their output is given by the multiplication of the input and by what is inside the block. And now that we are in the S world, we can benefit from all the nice properties of the Laplace transform, and in particular we can perform the so-called block operations that allow us to simplify the block diagram and find the relations between each input and each output. But remember, only because we are here, because the whole diagram is in the S domain, we can perform those operations. Those operations would be completely illegitimate in a diagram like this one with nonlinear relationships. So keep that always in mind. Another very nice property of block diagrams is that we can analyze independently the effect of each input in each output. So, for example, in a diagram with several inputs, x1, x2 of s, well, we could have here many interconnections. I won't draw all of them. Just imagine many blocks connected, a very complicated diagram, and finally we have maybe just one output. Okay, we can analyze how this input x1 affects the output just by assuming that x2 of s is equal to 0, and then performing maybe some operations and getting the overall transfer function between x1 and y. So we could get y of s is equal to some g1 of s x1, but that's not the only component of y of s. So the second step would be to assume that now x1 of s is 0 and study the relation between x2 and y, and that would be the second component of y of s, g2 of s times x2. This should have been 1. So you can divide and conquer when you study the problem. So in the next video we'll learn how to do block operations in a diagram in order to simplify it. But I'd like to emphasize that those operations, even though we like them because they're very intuitive, are just the same thing as algebraic operations. So we could get to the same result just by using common math. But as I said, they are very convenient, and we like to do things graphically, and that's why we'll learn that material in the next video.